Just getting started here. So we're just gonna wait just a little bit. Hopefully I don't have too much ADHD and I remember to either cut this later or make a chapter thing so you can advance. I think today we're gonna do 6502 programming. Maybe some other stuff too. Alright, this looks like it's all working. Yeah, it's working. Sounds good. So, how's everyone? For me, I think it's been a while since I made a video. I have this like real problem where time doesn't mean much to me. Like someone's at it could be that I haven't made a video for a month or it could be like a few days. It's really hard for me to tell. I don't think that's ADHD or autism, but it's something. And it's really weird because people, when you meet people for the first time, they're always like, "So, when did you go to your trip to Japan or whatever? Or when did you see your family last?" And I'll be like, "Maybe last year. Could be the year before." It's really cold here. So, yeah, that makes conversational awkward because people then give you that look like, "Okay, I'm trying not to look like I'm judging you, but I'm totally judging you." Hey Twitch folks, how are you doing? Do I know you? Or I can't believe there's 3 people already. And I'm not even doing anything yet. We're going to do assembly language programming on the 6502. So that'll be something. We'll see what that's about. Yeah. Got to do COBOL again soon. Hey Findus, how are you? Where's chat? There you go. Is it cold where you are? It's so cold here. I have so many layers on. I think I did my nails since the last time I was on. So yay, nails. I still have my Atari 400 mini here from the last time I took a picture. Too bad I don't have like a real retro computer, you know? I want to get the Spectrum. Yeah, I know there's no sun. In addition, like I wake up at noon and then by the time I'm out of bed and showered, it's like 4 p.m. because I don't know, I'm really like going slowly. The sun's basically down and there's nothing left to do, you know? So that's pretty depressing. I've been really unmotivated to do things, mostly because I think because I'm switching my medication. I take a few things for like mental health, and I made the really stupid decision, or probably, well, I think it makes sense, but I made the decision to kind of stop taking them. So one of the things I stopped taking was my ADHD meds, um, and my antidepressants. Like sort of like, well, what do you call it? Like reducing them to zero. Well, ADHD I just stopped, but it means that like without the ADHD meds, I'm just like so tired all the time. But I'm hoping that it gets back to normal. All right. So I'm just like always, I start out really tired, but we're going to get into it once we start programming and stuff like that. So where are we? I think we're doing, could be lack of vitamin D. I don't know about that because I take vitamin D all the time. I think I have it here. I take this vitamin D thing and it's like 1000 UI, I guess that's IU, fish oil and vitamin 3D. I don't know if 1000 is enough, but last time they took my labs, yeah, this is D3. Last time they took my labs, it was okay level, but I was taking higher concentration of D3 then. Now it's only 1000, but I'm guessing it's not terrible. It's not zero, you know, because yeah. Yeah, definitely like it's different than going out in the sun. Okay, so let's get psyched. Let's go. We're gonna write assembly code with Atari stuff. Let's see what we did last time. Alright, this all looks bad. It's like the wrong size. I think because I don't usually use the browser. There we go. That's a little better. We make this maybe a little smaller. And somehow we should make this wider, right? There we go. That looks good. We're all good. We're all good. That sounds so like Californian. It's all good. Oh yeah, we did some of this already. I ended up typing a lot, right? Oh, I got a comment on YouTube that told me how to like see the scrolling text. So let's try that out. Let's see. I think in D2 I have Visitor. Let me write this down because I'm totally gonna forget all this. So I have I get my little, I love these, just these like totally plain like paper things from Muji. They're just lines. Muji's kind of like Uniqlo if you have those, except they have a lot more like office stuff and skincare stuff and I guess furniture too. But I really like their stuff. Okay, Visitor 2.source. And we also have print screen. That's PRNTSC1.source. Hello. How do I say this? Exodicas. How are you doing? Are you an Atari fan or 8-bit fan, or are you gonna be like, what the hell is this thing? All right, so we have this, and now that means I can go to D1 and we'll have our Max 65 assembler here. And then I can load from our second drive, parent screen1.source. That loads it. And now I can list it, right? So here, like, it's too fast, right? So we can definitely do like list 10, was it 10 to 100 or something? No. List 10 comma 100. Yeah. So we can do things like this, but I think someone said I can hold F8. Nope. What the hell? Oh. Are you guys seeing this? Yeah, I guess so. It's kind of like pausing it. And Altair is sort of like doing something here. I didn't know what this is. But anyway, if I run assemble now, I can kind of pause it to see like what's going on. So it looks like it's printing out. This is my source code, and these must be the memory addresses, maybe? Let's see, this one says it starts at 5,000, so what does this mean? These are the values here, right? Oh, these are just saying what they're equal to, duh. Yeah, so it's just saying that EOL is going to be equal to 9B. All right. So here is the memory, 5,000. And it goes to 5,040. So what is this doing? 610, 5,040, 5,058. Looks like it's the last memory address used. 5,058. And these are just the values that it was assigning it to. So at least now I think I know what like the last value of. Oh, hey, yeah, so let's see. I'm a fan of programming language and a fan of learning. I saw your prologue video in my feed and now I want to check out the live stream. Yeah, God, I wanted to do more prologue. It was like so cool. Like, I know I did it almost nothing with it so far. It's just like facts and some direct like questions based on those facts, but like it was like, wow, this is kind of mind-blowing. It's basically like doing queries with SQL, but like in a programming language or more of a programming language. And I'm really curious like how Prolog can be used to like, how do you write sort routines with it? I just want to see how it looks and feel. Oh, I got allergies. Anyway, so that was really cool to find out about. Yeah, unusual programming is cool. It just like makes you think differently, especially like something like Prolog. Like, how do you think about the same problem, right? Like, when it's so different. And that's why I really liked functional programming for a while. I still do. I use Elixir mostly, but like, I started learning Haskell and it was like, wow, like, this is just so concise. And it's funny that like, I'm doing Haskell on one side and here's like 6502 assembly language on another. Anyway, so let's see, where do we go? Last time, the last video for Atari 6502, we started chapter 7 of Atari Roots. This book itself is a guide to assembly language for the Atari 8-bit computers. And you can get it online. In my other Atari videos, I have the link, and I'll add it to this one later. And so you can read it and follow along and do everything like I do. And if you have any problems, maybe look up the video or join the Discord and ask questions. It was a pain in the ass because like you had to learn a lot about Atari DOS and things that's not the programming language, you know? That's kind of like was the pain. But we've made it this far with some pain, and we're going to continue. So what we started to learn was how loops and branches work. And they said, just trust me, enter this program. It's called print screen, and they didn't really say how it works. They said they'll go into it later in chapter 12. But then this program uses the print screen code. And so like basically we'll learn how this works. So how it works, let's just make sure it compiles and works. So I just compiled the print screen program, right? Now I'll compile the visitor program. So I'll do enter. Oh, let's make sure that basic wasn't on. Was basic on? Let me restart this. Yeah, there's no basic here. So I'll do max 65420. We'll load the print screen program first. Okay, I thought, oh, it's on D2. There we go. We assemble it, and it's happy. And now we load in the visitor program and assemble that. VisTor, I think I called it, right? VisTor2.source. Yep. And then we assemble this. And then we can go back to Atari DOS with CP. And we can run our debugger, bug65. And we type G617, I think, to start the program. And there we go. Take me to your leader. That was the program. It prints that on the screen. So let's see how that works. We'll go to the next part now. I think we read this. Yeah, it wouldn't be a bad idea to save it too on the disk, and I saved it already. After you've run and saved the program, you'll know exactly what it does. So now we can explain how it does what it has done. We'll start with an explanation of the assembly language .byte directive, which you'll see in lines 10 to 120. So maybe it's good to load this program up in here so that we can see it. Enter D2 VisTor2.source. And we'll do a list 100 to 120. There we go. So we see these commands. This text here is a label. So it just means we can reference this later. And then everything else here are just byte commands with a bunch of hexadecimal numbers. Looks like nibbles, right? So, which is what, 4 bytes, right? 4 bits? Anyway, look at this picture. I like kind of old drawings. It reminds me of like old D&D books. There's a little spider here. Looks like some sort of like inspector from like Pink Panther or Inspector Gadget or something. And here's like Elvira from like Addams Family. Is that her name? I don't even know. The byte directive. The byte directive is sometimes called a pseudo operation code or pseudo-op. I would have just called it pseudop. Wouldn't that be easier? Pseudop. Because it appears in the opcode column of the assembly language source code listing, but is not actually a part of the 6502 assembly language instruction set. Instead, it's a specialized directive designed that this is weird English. Instead, it's a specialized directive designed that can be used with some assemblers but not with others. I'm like getting stuck on the English here. Anyway, for example, .byte works with both the Mac65 assembler and the Atari assembler editor, but it does not work with the Atari macro assembler and text editor. Luckily, we're not using that one, huh? When you write a program with the Atari macro assembler and text editor, you have to use the letters DB in place of the .byte directive. Other pseudo-ops also differ from assembler to assembler. There are no generally accepted standards for writing pseudo-op directives, so pseudo-op codes designed for one assembler often won't work with another. Well, luckily for us, it works for both of them. Hey, why does this cut off now? Guys, when did this go bad? Let's see. So strange. Um, I want it to be around like this, but somehow it's cutting off at the edge here. So let's open this up. And then we can make it a little smaller. And then we can make this one a little bigger. Alright, I have no idea when that happened, but it'll be a mystery forever and ever. What the byte directive does. When the .byte directive is used in a program created with the Mac65 assembler or the Atari assembler editor, the bytes that follow the directive are assembled into consecutive locations in RAM. In the program called the visitor, the bytes that follow the label text are ASCII, Atari ASCII codes for a series of text characters. All right, that makes sense. I'm just like so stuck on this here. So a 2 character hexadecimal. So a single hexadecimal can go up to 16, right? And to do 16 in binary, you need, well, it can go up to 15, right? And to do 15 in binary, you need 4 bits, is that right? So you have 1, 2, 4, 8. Yeah. So that is 4 bits for 1. So 2 would basically give you 2, this would be 8 bits then, right? So each one of these here in hexadecimal is 8 bits then, right? So this represents an 8-bit. Oh yeah, I mean, God, I should just read, right? It says byte, so it's an array of bytes. It's a list of bytes. And I'm here like trying to do stupid math, right? 4 bits are a nibble, yeah. But here we're this thing with 2 of these is a whole 8-bit, and if it were just 1, then it would be a nibble, right? So okay, that makes sense. Sorry I blanked out there. Sometimes that happens. Sometimes the brain just stops working. It's like, what are you talking about? Math. We need more coffee. It's like, it's almost 8 p.m. and I'm not awake yet. Braining is so hard. It's a wonder I'm functional in the world. Looping the loop. Well, that sounds like a special, like, advanced maneuver. As we explained in chapter 6, the X and Y registers in the 6502 chip can be progressively incremented and decremented during loops in a program. Yes, we saw dec X and inc X, or inc Y and dec Y, so we know how to do that. In the visitor program, the X register is increment. Okay, so the brain's starting to brain. So this guy's the visitor. He's visiting. And he's saying, take me to your leader. That's why I said, take me to your leader, right? That seems kind of sexist. It's like, what? He saw a woman and was like, hey, you can't be the leader? The fuck? Push as fuck. Oh, God. All right. All right. Let's get back to business. All right, in the visitor program, the X register is incremented from 0 to 23 in a loop in which the characters in a text string are read. The characters that are to be read are written as ASCII codes in lines 100 to 120. So here, each one of these 54, 41 represent take me to your leader. So, yeah. That makes sense. let's see here. So this 54 should be a T, right? The 54 should be a T. So let's look up ASCII chart with hex. And so we have a T54. Look at that. Hexadecimal 54. And then the next one should be A41. 41 hexadecimal A. There we go. Take me to your leader. We'll have to believe that the rest is actually correct. It is an exercise left to the reader, but we've proven it. We wrote the code. Okay. So when we say we're looping in line 160, let's go look at the program again so that we can see what it looks like. Here's the loop. So the loop starts here. We set the X register as 0. Then we load the accumulator with from the text address, but offset by whatever's in the X register. Then we store that in the text buff location, offset by X, and then we increment X and we copy X. No, oh, we compare, not copy. Compare X with 23. And if it's not, yeah, so we're basically looping until we see 23. Compare the X register with 23. So here we go, incremented from 0 to 23. That's what that compare X to 23 is about. The characters that are read are written as ASCII codes. In line 160, the statement load X number 0. This is number means immediate, I think. So it's just literally the number. It's not an address. Is used to load the X register with a 0. Then in line 170, the loop begins. Yeah, because it says loop here. Incrementing the X register. The first statement in the loop is load accumulator text comma X. Each time the loop cycles, this statement will use indexed addressing to load the accumulator with an ASCII code for a text character. There's a fun thing with increment X and decrement X. They set the 0 flag. So if you make sure the end of the loop is 0, you don't need to compare X. Look at you. So basically it's sometimes better to count down rather than to count up. That's really what it means, right? Because counting negative to 0 doesn't make too much sense. I guess it could be done. All right. When the loop ends, all the characters in the text buffer will be printed on the screen the first time the program hits line 170. There will be a 0 in the X register since the 0 has just been loaded into the X register in the previous line. So the first time the program encounters the statement load text comma X, it loads the accumulator with a hexadecimal number 54. That's this 54 here. Hey Akram203_RR, welcome. We're doing Atari assembly programming. This is chapter 7, I think, in Atari roots. So we're kind of doing loops and branches, conditional logic. What programmers sometimes call the 0th byte after the label text. There's no need for a number symbol in front of the number 54. Incidentally, since numbers that follow the byte directive are always interpreted by the Mac65 and Atari assembler editor as literal numbers. All right, so they're kind of exceptions. Bytes cannot be dereferenced in memory, so they're always assumed to be direct numbers or literal numbers. How do they say it? Literal numbers, yeah. Hey, Blocks Hub Roblox, welcome. Welcome back. It's like the gang. I'm doing pretty well. I was saying earlier that I was so tired because I stopped taking my ADHD meds. Because I didn't say why I stopped taking it. I stopped taking it because I started getting little twitches, I don't know, my shoulder or whatever, and I was like, this is really bad. I was kind of freaking out, so I was talking to my psychiatrist and I was like, "Hey, I'm starting to twitch." And she's like, "Yeah." I'm like, "Well, that's bad, right?" And she's like, "Well, you know." I'm like, "You know what?" She's like, it's it's all right. Like, it's not all right. So, anyway, long story short, I'm stopping most of my medication to kind of just figure out which one's causing the twitch, but it's really annoying. You asked how I was doing. People ask an autistic person how they're doing, they get a real answer. I'm doing great. The weather's been good. Food's been good. I don't know. What do people say? I listen to some music. It's all good. My sports team won. I don't even know what sports are playing right now. It's winter, right? There must be hockey. And what's in Europe? It wouldn't be football, right? No football right now. It's too cold. Rugby? Yeah, that's about it. Tennis? No, there's no tennis. I don't know. Maybe it's sports break for the winter. All right. Well, if people in chat know more about sports than me, you can certainly tell me what sports are being played right now. Okay, so where were we? Incrementing and decrementing the x and y registers. Now let's move on to 190. Where's 190? Increment x means increment the x register. Since the x register currently holds a 0, this instruction will now increment that 0 to a 1. Next, in line 200, we see the instruction compare x number 23. That means compare the value in the x register to the literal number 23. The reason we want this comparison to be performed is so we can determine whether 23 characters have been printed on the screen yet. There are 23 characters in the text string that we are printing, and when we've printed them all, we'll want to print a carriage return and end our program. I'm guessing the 52 here is a carriage return? No, the 21 must be a carriage return. I didn't see that. The 21. Right? 21's carriage return. That would be decimal, right? No. Hex? Was it in hex? Where was it? No, it's hex. Hex 21. So that would be over here. Oh. 21. Whoops. Why is it not carriage return? It's probably a task key's different, huh? 33. Where's carriage return? 13. Let's look up a task key. Okay, so this is just to take me to your leader exclamation point. Where's the carriage return? Load, compare 23, jump subroutine print line. I bet print line does the carriage return. Right? Bye, Unlink. Oh, no, it's not Unlink. It's S Exodicas has to go. Unlink's I have no idea what sports are being played. No, 20's 20? No, 19 would be the new line, no? Well, I don't know. But this 21 here is the, do you see it? Is it being highlighted? Yeah. This 20 on line 110 at, the 21 is the exclamation point. So this is take me to your leader, and it needs a new line. But I bet it's in print screen. Here, let's take a look. You're not stupid. Did you see what kind of things I've been saying? Let's look up the code for print screen, because after this is done, you see it goes to print screen, right? Or open screen and then print line. So let's look up that. Open screen print line, that is 531. So here's open screen, da 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 da. This doesn't look like it's doing anything to do a. This looks like store line, maybe. I bet in here somewhere is doing a new line, but I'm sure we'll run into it soon. They're explaining this, and they're explaining it like in a lot of detail. So I'm sure in chapter 12 they'll talk about it. All right. We did this. Then we'll want to print a character return. Comparing values in assembly language. There are 3 comparison instructions in 6502 assembly language: CMP, CPX, and CPY. CMP means compared to a value in the accumulator. So you can only compare a value, like the parameter that's passed to CMP, with what's in the accumulator. When the instruction CMP is used, followed by an operand, the value expressed by the operand is subtracted from the value in the accumulator. This subtraction operation, so wait, it's the operand is subtracted from the accumulator. So it's accumulator minus operand. Okay. A minus O. AO. The subtraction operation is not performed to determine the exact difference between these two values, but merely to test whether or not they are equal, and if they are not equal, determine which one is larger than the other. If the value in the accumulator is equal to the tested value, the zero flag of the processor status P register will be set to 1. If the value in the accumulator is not equal to the tested value, the Z flag will be left in a clear state. If the value in the accumulator is less than the tested value, then the carry flag of the P register will be left in the cleared state. Oops, sorry. Okay, so if it's less than, then the carry flag is clear, because it didn't need to do any borrowing to subtract, right? So you do 5 minus 1, it's 4. There was no carry being used for it. If the value in the accumulator is greater than or equal to the tested value, then the Z flag will be set to 1 and the carry flag will also be set. This seems false. If the value in the accumulator is greater than or equal to the tested value, then the Z flag will be set to 1. Ah, yeah, that part's true. And the carry flag will also be set. So if they're the same, then the carry flag's going to be set. All right, I believe it. CPX and CPY works exactly like CMP, except that they are used to compare the values with the contents of the X and Y registers. They have the same effects that the CMP has on status flags of the P register. So I assume it's basically comparing it with the X, so it's like accumulator minus, no, it's X minus the number. So it replaces the accumulator. Seems like a pretty good book. Yeah, it's like really made for people who don't know programming and also don't know anything about the 6502 assembler language and know nothing about, like, yeah, just about nothing. So what's good for us is, because I know nothing about Atari, it kind of really like is gentle about what it expects you to know, even though I still had lots of problems just knowing how to like copy a disk, or because I just don't know these things. But in general, it's been good. because the other books are like, you get a 6502 book, it'll assume you know how to use, like, each computer is different, right? So here it tells you, here's how to do it with your assembler, your macro 65 assembler or the Atari assembler. So that's kind of nice. Yeah, so, maybe there's a better book for you, but this kind of just makes zero assumptions. The bad part about this book is, like, God, you see how slow they go through stuff? But, that's okay. We're just here for chill vibes anyway. We'll eventually get there, just slower. All right, using comparison and branching instructions together. The three comparison instructions in Atari assembly language are usually used in conjunction with 8 other assembly language instructions. Wow, that's a lot. The 8 conditional branching instructions that we mentioned in chapter 6. The sample program that we have called the visitor contains a conditional branching instruction in line 210. So let's see line 210. What does it say? BNE loop. So branch if not equal to the label loop, which is line 170. That instruction is BNE loop, which means branch to the statement labeled loop if the 0 flag of the processor status register is set. I'll say branch not equal. It's so much faster. This instruction uses what can be confusing convention of the 6502 chip. In the 6502's processor register status registers, the 0 flag is set equals 1 if the result of an operation that has just been performed is 0. And the 0 flag is cleared equals 0 if the result of the operation that has just been performed is not 0. Yeah, but if you think of the command as branch if not equal, then you don't have any of these like confusing like what to do with the Z flag. I just don't care. It doesn't really matter. It really doesn't matter. That's what I was just saying. This is all quite academic, however. As far as the result of the statement BNE loop is concerned, when your computer encounters line 10, it will keep branching back to line 170, the line labeled loop, as long as the value of the X register has not yet been decremented to 0. What? Have they gone insane? Do you guys see the problem here? I'm so confused. It's saying that we're decrementing has not been decremented to 0, the X register, right? But here, we're incrementing the X register. Once the value of the X register has been decremented to 0, the statement in 210 will be ignored and the program will go to line 220. Guys, am I insane here? Where are we decrementing the X register? This is crazy. I think they're just wrong. Anyway, let's assume it'll loop to 0. Yeah, it'll eventually loop to 0, but that's not what's happening. It's comparing it with the number 23. So increment x is going to keep getting bigger one by one until it gets to the number 23. And then we subtract what's in the X register, which is 23 minus 23, which sets the 0 flag. Maybe what they're trying to say is that once the comparison is 0, or the status flag is set. Yeah, that's crazy, right? Do you think I should write to the editor? All right. Yeah, we can be pedantic. In line 220, the program will jump to the subroutine open screen, right here, open screen, which currently resides in RAM beginning at the memory address 5041, provided the object code for both printsker and visitor have been loaded into your computer and are ready to run. That was the other program we compiled beforehand, and it just knows that the subroutine's in that memory location. If you don't know why and you'd like me to explain, please let me know. Yeah, tell them. I'm gonna write an email. Conditional branching instructions. Uh-oh, this looks boring. Boring as fuck. All right, let's just get through it, all right? We can do this. As we pointed out in the previous chapter, there are 8 conditional branching instructions in the 6502 assembly language. They all begin with the letter B, and they're also called relative addressing or branching instructions. I think I'll call them branching instructions because they start with B, right? These 8 instructions and their meaning are BCC, blind copy. Branch if the carry flag of the processor status P register is clear. If the carry flag is set, the operation will have no effect. Do you guys remember what the processor status register is? Maybe we should look at it real quick so we can remember it. Yeah, it's just a register filled with flags. But I think, did I put it in my gist? Let me see. Just give me 1 second here. Here's my gist. Where did I put it? It would probably be under maybe general. Nope. No, we didn't put it in here. But let's look it up because I think it's gonna matter one day for us. It's inside the 6502 page 43, which isn't exactly here, but it'll be close. Here it is. Oh, you guys don't see it. There we go. All right. X register, Y register, blah, blah, blah. Processor, here we go. Layout of this register, here it is. And then they print it out. I think where's just a summary here. 4 of the status bits are called status flags. They are the carry flag. Well, is there something that shows this better? Okay, so here is all the registers and stuff. So here's the X register, the Y register, the accumulator, and the processor status register, the program counter, I think it's called. I forget what SP is. Damn it. I almost remembered it all, right? And then in here you see the processor register are just flags. So it uses, instead of a number, like these just hold one number, this has 8 different bits. 1, 2, 3, 4, 5, 6, 7, 8. But it looks like one of them isn't used, so it means there's 7 bits being used. And let's see what they are. Oh, its stack pointer was the SP. I forgot about that one. We haven't really used that yet. I'm like going all over the place. 4 of the 5, where does it say this? It isn't used for storing. These 4 flags, 3 of the P are their bits called condition flags. So let's see if we can like just copy this. It's like PDF, so I don't know if it'll actually copy, but let's see. and then we can just post it in here under, maybe we'll do it under 65026. We'll make something called 6502 CPU, and we'll do this. There we go. So we'll call this the P register. There we go. So now next time, if we ever need it, we can look it up pretty easily. All right, where were we? We're on page 117. Okay. Branch if the carry flag of the processor status P register is clear. If the carry flag is set, the operation will have no effect. Branch if the carry flag is set. So this is just the opposite. So it's really not like that different. Branch if the result of an operation is 0, BEQ, if the 0 flag is set. BMI, body mass index. Branch on minus if an operation results in a set negative N flag. BNE, if branch if not equal to 0, if the 0 flag isn't set. BPL, branch on plus if the operation results in a cleared negative flag. BVC, branch if overflow flag is clear. BVS, branch if overflow flag is set. What's the difference between overflow and carry? That's something we have to figure out. They sound like the same thing to me. All right. How conditional branching instructions are used. Oh, now I'm getting hot again. Wow, you know, it used to be that I would have more people on YouTube than on Twitch. And I thought, no way anyone's going to be interested in this on Twitch. Like, Twitch is like, you know, everyone's watching video games like Valorant or whatever, right? But now I have, I mean, it's not a big number, 5 versus 1 on YouTube, right? It's kind of interesting how that can happen. All right, to use a conditional branching instruction in 6502 assembly language, the usual method is to load the X or Y register with a 0 or some other value and then load the A register or a memory register with a value to be used for a comparison. All right. After that is done, a conditional branching instruction is used to tell the computer what P register flags to test and what to do if these tests succeed or fail. This all sounds very complicated, and it is. Actually, I don't think it is. I think they make it sound a lot more complicated than it needs to be, because when you need to like compare something, you kind of know what you're trying to compare. You know, like here, you got the X thing, right? So you got X incrementing and you want to compare it with the number 23. So which one are you going to use? Are you can do like, you got branch if equal or branch if not equal, right? So you kind of have to choose how you want to do it. All right, where was I reading? And it is. But once you understand the general concept of conditional branching, you can use a simple table for writing conditional branching instructions. Here's one such table. Oh my God. Yeah, so this is saying like, hey, if you're doing it with a value or an address, then you're going to use the accumulator, right? And if you're doing it with a value, then you put the number sign in front because it's a value. And then if you're doing it with something that's in a memory address, you put a dollar sign. And here it's saying Same thing with the X register, same thing with the Y register. So I really don't think it's that complicated. Let's just skip all of that because I think it'll just make sense naturally once we start using it. Assembly language loops. How much longer do we have here? This is my ADHD. Oh my god. Oh my god. Page 128 and we were on like here. So we got about like 10 more pages. Assembly language loops. In 6502 assembly language, comparison instructions and conditional branch instructions are usually used together. What are they saying here? Comparison instructions and yeah, obviously. If you don't compare, then it means you just want to jump no matter what, and that's probably less common than to basically do a loop or a jump based on a condition. In the sample program called the visitor, the comparison instruction CPX and the branch instruction BNE are used together in a loop controlled by the incrementation of a value in the X register. Each time the loop in the program goes through a cycle, the value of the X register is progressively incremented or decremented. No, it's only incremented in our program though. And each time the program comes to line 200, the value of the X register is compared to the literal number 23. When that number is reached, the loop ends. The program will therefore keep looping back to line 170 until 23 characters have been printed on the screen. Then in lines 220 and 230, we'll open your computer screen, clearing it in the process, and we'll print the string that has been transferred to the text buffer on the screen. Finally, at line 240, the program will go into what's known as an infinite loop, cycling back to the same jump instruction over and over again, and doing nothing else until you push the break key or in some other way halt the program. And that's infin for infinity, jump infin. Why use a buffer? Before we move on to our next topic, improving the visitor program, it might be worthwhile to answer a question that may or may not have occurred to you. The question is, why use a text buffer? Why not just print the text in lines 100 to 120 directly into the screen without moving it first into a buffer and then out again? Here is the answer to that question. Text can be loaded into a buffer in many ways, from a keyboard or from a telephone modem. I want a modem now. Do you think like if we had a modem, we could actually like call someone with it? Are there like still numbers you can call with a modem? I'm actually not sure that I could hook a modem onto like my phone system because it's all digital. I don't know how that works. For example, as well as being loaded in as data directly from a program. And once a string is in a buffer, it can be removed from the buffer in just as many different ways. Another advantage of a text buffer is that you can load it into RAM, note its address, and use it from then on whenever you like. A buffer can therefore serve as a central repository for text strings, which will then be accessible with great ease and in many different ways. Which means that it's kind of weird. Like, we have text here, right? In the text line. Why don't we just use the data here instead of moving it to a buffer? Why are we just moving this to another place? It's already here. Why don't we just load it into the right place? You know what I mean? Do you want to try that? Because we're putting it in text buff, right? Text buff is 5041, right? 5041. Oh crap! I did not mean to do that. I hit reset by accident. They need to be in video RAM probably. You can only have your data in ROM. Oh, so the byte stuff can only be in a special area? Right, so like what I'm wondering is, what if I change this here to the other address, 5041? What if I go, oh, I can't go up? Why can't I press up? Anyway, I can't change it. So what if I go 80, 5041, right? So this will put it in 5041. And then why don't I put this? I don't know. Can I do it twice? Can I do like 130 and then do it again? And put it at $0600? You think this will work? So now it looks like this. 5041 for this code. And then 130 here. Let's see if the assembler lets us do this. Let's do that again, but this time I want to stop it. So 5041, yeah, that's fine. But notice here, it's putting it, it looks like it's putting it in address 5041, right? Yeah, you see 5441. And then I make it 600. It looks like it switches, you see? Now it's in 600. But the problem is, the code should no longer have to do this loop. So I think that means that I can basically clear all these lines. Oh no, I want 220. So, like, I don't even need 160, right? Probably I don't need 160. Yeah, I don't think I need 160. So there we go. We assemble this. And how did we run it again? It was like... Shouldn't it be G600? No, it was not G600 because it didn't, we had some byte stuff in there. So we had to skip over that. But now I should be able to just do G600. So let's see what happens when we run this. Hopefully I still have the other code loaded in. Look at that. Doesn't it seem like it still works? So, I think it works. So this whole example is sort of contrived. I've optimized it. All right. I'm gonna write more letters to the editor. All right, let's try to understand what's going on here. I am the leader, you fool! Okay, I don't see what this guy now has any... These medieval guys have anything to do with the inspector guy coming to visit the vampire lady. Like, guys, help me understand it. All right, improving the visitor program. Now we're ready to make some improvements in the program called the visitor. Yeah, just remove a whole bunch of lines like I just did. That's the improvement. I think once I was working with a guy and he wanted to optimize his code, and literally I just removed a whole bunch of code and it still worked. I was like, oh my God, it was like so perfect. But it's a little humiliating, you know? You don't want to like seem like a jerk, but what do you do when you remove someone's code and you're like, okay, now it's just a lot better? Not that the program doesn't work, it does, but it has certain limitations, and some of those limitations could be removed quite easily, as they have been in this new program which I've called Response. Response is quite similar to the visitor, but as you will soon see, significantly better in several ways. Oh, look, they have a string here. You didn't need to put the byte thing in there. All right, so let's code this up, right? And I hope you do. You can type it into your computer's memory. All right, let's do it. First, let me just do a hard reset. So we have everything cleared from memory. That's Shift F5 if you're using Altera. Do you guys hear the little like click click noise from the Atari? So we're gonna start this. I have an Azerty French keyboard, so it's like so annoying that I have to press Shift to do like so many things like number signs, all the number stuff. I have to press Shift. 50401. I'm so bad at typing stuff, like, especially when it's abbreviated. So please help me. Someone helped me last time and it was like a lifesaver. (9B). Two spaces here because now we're using an actual sort of opcode. It's a compiler directive. It's saying to start our code in memory address, store the code. Hey, I'm going to remember this time. We need to give it a compiler directive called opt_obj because this tells it to store the code in memory after it's assembled it. I'm getting a lot of messages, but nothing important. All right. Where were we? 100. 110 is nothing. 120 text is a label here, so only one space. Dot byte. I can't type lowercase. Is there a way to type lowercase? I don't know how to do it. Any of you have Ataris know how to type lowercase? RSPONS. Response. Response. 160. So here we're loading the X register with the number 0 directly. Oops. We need two spaces here for load X number sign 0 because it's an opcode. Then 170 is the loop. That's a label, so only one space. 180, load the accumulator with whatever's in text, address, offset by X, kind of like what we did in the old code. Uh-oh, I made a mistake. Someone said I can press up and retype it, except my up arrow key does nothing. So I don't know how to do that either. 180, 190 is store into the text buffer address offset by X, or just moving stuff. Store whatever in the accumulator into the text buffer address offset by X. 200 compare. Oh, now we're using compare instead of branch not equal. Right? Compare 9b. Okay, so whatever's in the accumulator, we're checking if it's equal to 9b. And remember, 9b in line 80 here is the end of line character. So it's basically saying if the accumulator, compare what's in the accumulator with the 9b number, right? And then it says if it's equal to that number, then branch to fini. Are they French? And otherwise, increment the X, register. I did it again. I typed the same line number twice. Increment X, line 220, 230, jump to loop. So we're just looping here. And 40 is the fini label. 250 is jump subroutine open screen. And then 260 is jump subroutine print line. And then we're going to come back, and then this is infinity. Jump infinity. The last code we just did this in one line. It was like infin space jump infin, but for some reason I guess it's just prettier to make it like this. Let's save this. And this is called response. Just response. Yeah, let's store it as response. Response dot source list will print it, right? Yeah. Okay, so it saved it. So let's look at the assembled stuff again. So we have these are not, this is not code, these are just like constants that it's setting. And then we're saying here start with memory address 650. So here the text starts at 650, but our code starts in 66B. Yeah, our code starts in 66B. And it ends in 681. So let's write that down. 66B to 681. Ah! I just reset. Why am I so... But we've assembled it, so it's in memory. We just have to load that print screen file so we can load, print SC1. Okay. All right, so now we have this. And now we should be able to run this in bug65. The program was in 66B, right? So let's look at that, 66B. Yeah, it looks like there's a program there, and in 600 it should look like wasn't it in 600? I'm a little confused. Oh, 650. It was in 650. Display 650. Yeah. I am the. You see, so the code is in there. I am the leader, you fool. So how do we run? If you want to run the response program, and I hope you do. Yes, we do, right? You can type it into your computer's memory right now. Since it calls the same subroutines that its predecessor did, you can assemble it and run it as soon as it's typed, provided you still have the program called print screen is loaded into RAM. To run the response program, you can go debugger, la 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 la. Should be able to run 66B, right. So let's do that. G66B. Almost. Well, that's interesting. Why did that happen? Response.source. Where did we go wrong? Maybe I typed the program in wrong, right? Response. I didn't type it right. Right. Let's list this. I guess let's list it slowly and compare it. Response text buff equals 5041, open screen 5003, end of line on 89B, 95 option obj, 100 0650, text.byte I am the leader you fool, 140 RSPONS, 160 load x number 0, 170 loop, load accumulator text comma x, 190 store text buff comma x, 200 compare number sign dollar sign 9b, beq branch equal fini increment x, 230 jump loop. Yeah, that's 170. 240 fini. 250 jump subroutine open screen. 260 jump subroutine print line. 170 infinity. 280 jump infin. That seems correct, right? I feel kind of bad, like it should work. Starting to piss me off. Go 66B. You guys see that? It didn't go all the way. Aha! It's expected. I don't know why it didn't work the first time. But it didn't print all of it. Provided that you've typed and assembled it in accordance with the suggestion that I've provided, even if you followed the instructions through, you'll still encounter one small problem. Only the first 23 characters of the string, I am the leader you fool, will print on your computer screen. That's because the text buffer we created in the program print is only 23 characters long. The flaw is easy to remedy, but before we fix it, it might be a good idea to save response on a disk in its both source code and object code version. All right. We've already saved the source, so I'm not going to deal with the object. Fixing the print screen program. Now we're ready to lengthen the text buffer used in print screen program so that it will print its complete message on your computer screen. To lengthen the print buffer, just put your assembler into its editor mode and load the program source code into your computer's memory. Then you can change line 70 from bufflen equals 23 to bufflen equals 40. When you've made this change, you can save the amended source code under the file name print_sr2, assemble the program, and save the object code under blah blah blah. When you've saved your programs, you can reload the response program, run it with this instead. This time you should see the full string on your video screen, but unfortunately you'll now notice something else wrong. After the line, "I am the leader, you fool," you'll see a line of little hearts. How did they get here? All right, let's try to do this first. So we get out of this. We go back to the Max65 compiler. And we load our print screen1.source program. We can list line 40 to 100 here, and bufflen is 23. So they say change it to 40. So we're going to do 70. Bufflen is equal to 40. Is that how it looks? I think that's how it looks. And now when I compile it, bufflen is 40 now, which is hexadecimal 28. That looks good. Let's save this program as print screen2.source. We've already assembled it, so now all we should have to do is just rerun our previous program, which started in 66B. So let's try that. Go 66B. Oops. I wonder why it does that. Go 66B. It's still not happy. Maybe it's the order that I'm doing things? Let me try seeing if I compile the visitor program, if it'll like work. Was it 2? Visitor 1? I forget what it's called. No, we don't want visitor, we want a response. Crap, was there a response too? This one has what did this change? I think this is just response. Alright, let's try this. G66B. Oh, okay, now we see it. Maybe it's the order. Maybe I can't compile the first program second. I don't know why that would be though. Alright, I am the leader, you fool. Now we have the hearts. We did this. We did all this. Little hearts. How did they get there? I'll answer that question in just a moment, but first let's take a look at some of the differences between the program called the visitor and the one called response. A better routine. Gotta finish my coffee. From a technical point of view, the response program is better than the visitor for several reasons. The most obvious difference between the two programs is the ways they handle the text strings. Yeah, because we were using the we're using the we just put in a literal string with quotation marks. In the program called visitor, we used a text string made up of ASCII codes. In response, we used a string made up of actual characters. That made the program much easier to write, and it makes it much easier to read too. Another important difference between our newest program and its predecessor is the way the loop is written. In the program called Visitor, the loop counted the number of characters that had been printed on the screen and ended when the count hit 23. So it's like if you did a string length first and you knew it was going to be 23 characters, and then you loop to string length, right? But instead here, it's kind of doing it like the way C does. How does C do it? It's like it's looking for the null character, right? So it's basically going through a string, each letter, until it finds 0, and then it knows it's the end of a string. So we're using EOL as the end of a string, so we're looking for that. Now that's a perfectly good system for printing text strings that are 23 characters long. Unfortunately, it isn't so great for printing strings of other lengths. So it isn't very versatile. It's not a very versatile routine for printing screen characters on a screen. Testing for a carriage return. The response program is much more versatile than the visitor because it can print strings of almost any length on a screen. That's because it doesn't keep track of the number of characters it has printed by maintaining a running count of how many letters have been printed on the screen. Instead, each time the program encounters a character, it tests the character to see whether its value is 9B, hex 9B, the ASCII code for a carriage return or end-of-line character. If the character is not an EOL, the computer prints it on the screen and goes on to the next character in the string. If the character is an EOL, the EOL is printed on the screen and the routine ends. And that's that, except those pesky little hearts that we encountered when we ran the response program. Now we'll take another look at those hearts and see what we can do about them. Yeah, I have no idea what those hearts are. I see, because we made a string, we didn't like null it out, the text buffer. The hearts are there because the text buffer we have set up for our visitor and response message is now 40 characters long, longer than either of our messages. And the part of the buffer that's left over is filled with zeros, as empty memory locations in computers usually are. Then why the hearts? Well, in a ASCII character code that your Atari uses, a 0 does not equate to a space. Instead, it equates to a heart-shaped graphic character. The ASCII code for a space is hexadecimal 20 or 32 in decimal notation. Just look at ASCII character string in the visitor and response programs. You'll see that the spaces in the message "take me to your leader" are indeed represented by the value 20. It is possible, of course, to print messages on your Atari screen without strings of hearts appearing after them. What you have to do is keep the hearts from appearing is clear your text buffer, or more accurately, stuff it with spaces before a program runs. So here's it that will clear your text buffer. Should we try to write it ourselves? Where was our text buffer? It was in 650, right? Let's take a look at it. That was response.source. Yeah, you can see it's in 650 is where the buffer begins, where the text begins. And then we can just like clear it out. So let's try to write a program that does that, huh? Do we know enough yet? So let's do 100. Oh, where do we write our program? Let's put our program in 66B like the other one. We'll run our program first and we'll load 66B. but in that case it should be zeroed out, right? Let's see if this works. Opt to do this, and then we store it in hexadecimal 66B. And then we want to set our register to our X register to be 0, right? What is that? Load X 0. And then we want a loop. I have an alarm that goes off at 9 p.m. just to ask me if I've eaten, because sometimes I just don't remember to eat. And then I like start falling apart and I don't know why, and I'm like, oh, I'm sick. Sweetheart, why am I sick? What's going on? And then I try all these things and I realize, oh, I just haven't eaten. Okay, so now we want to copy the number 0 into this address. So I guess we can just load into the accumulator the number 0, right? This is probably a better way to do it, maybe. And then we can just store that into it's 650 offset by X. So that'll put a 0 there. And then we check if we just stored that there. Load accumulator. Do we increment the accumulator first? I want to know how I think we normally increment the accumulator first, right? No. I think here... No. We want to do compare... What's the compare with X thing called? CMX? CPX. Compare X with 40 because we want to clear 40 characters. And we say if it's not equal to 40, then we go to loop. Branch if not equal, go to loop. Otherwise, we increment X. Oops. Compare to 40. I think I need to increment it after I store it. Otherwise, it'll never increment. So it looks like this. Increment X, compare X to 40, and then branch to loop if it's not equal. Otherwise, I'm done, right? I think I can just end. So let's try to save this as clear.source. No, it's not enter, it's list. I almost really screwed myself. List d2 clear.source. So this will save, it'll save it, right? Yeah. And now let's try to compile and see if it compiles. Yep. So here it starts in address 66B and it ends in 677. and it's going to clear address 650. So let's see if this works. Bug 65. My code is in 66B. There's our code. And 650 is the buffer, right? I am the 50, 1, 2, 3, 4, 5, 6, 7, about 8. I am the leader. Oops. You fool. And then you see after fool it has stuff. So that's at 668. You can see that it has garbage in there. And after I run my program, it should no longer have garbage in 668. Like all of this should be clear. So let's try running it. Go 66B. Oh crap. Maybe that's how it goes until you tell it to break. Now let's display 650. It's all empty. 668 is all empty now. But in my code where it's 66B, where's my code? Why did it clear my code? Maybe it's too long. Anyway, let's try going back and now loading the response program. Max 65 420. We load that program, which is enter the. Actually, let's load the print screen just to be sure. We assemble this, then we load the other program. Okay. Ay, ay, ay. All right, so I failed. Fool, question mark. Oh, it's really close where our code begins and the other stuff. Oh, does it overlap? It might. Anyway, let's see what they do compared to our code. Okay, so they have fill load accumulator with fill character, whatever that is, right? Load X with buffer length. Oh, here they're decrementing X. I'm incrementing X. So this is 40. Start. Decrement X. Oh, they have return to subroutine. Maybe that's better. Store accumulator text buff, which is the same number I have here, right? Comma X, branch not equal start. So it's very similar. Oh, I put in 0, which is the exact wrong character. I need to put in 23 for the fill character, which is the space. Or 20, right? I'm so stupid. That's why it'll print hearts anyway, because the whole point was that I wonder, how do I go up? So maybe I should have done it like this too. So then they're going to have to call fill to start this thing first. Jump subroutine fill. Yeah, and then it jumps to fill. Yeah, that makes sense. So let's try that without looking. Let's start that over again. Woo! We can do this. Wait, is it visitor pro? No, it's the response program that we're changing, right? Oh. Incorporating it into your visitor program and response program. Why are we doing it into visitor? Oh, here's response. All right. Let's try. It's hard writing assembly because you can't just like use an IDE to do things. It's kind of crazy how much harder it kind of feels because of that, you know? Oh crap. I am an idiot. Alright. I meant to press F8 to stop it. Okay, so we're gonna need a new constant for bufflen. So I don't think there's anything in here for that, right? Oh, here. So we'll put it under like 65. Bufflen is equal to 40. 65 bufflen is equal to 40. Okay. So now we have our buffer length set to 40. Do we need anything else? Oh, we also need a character that is the clear character, the fill character, right? So let's put that as 66. Fill character is equal to, was it 21? Or was it 20? I'll assume it's 21. We can look and fix it later, right? Okay, so we have that in here. And now we want to add our code somewhere in here. They put it pretty low, like pretty high in here. Like we'll call it fill. So that's our label for our fill code. And in the fill code, we're going to load the X register with the value bufflen, right? That was from the constant that we made earlier. I think that's right. And then I guess we want to load the fill character into the accumulator. I don't think we want to loop. We don't start the loop yet because the fill character is always going to be the same. So we can just load that into the accumulator. What's it called? Fill character? I think just fill ch, right? All right. And now we want a loop, I think. So 1330, we can say f loop. And in here, we basically store the accumulator into the what's it called? The buffer text buff. That's what it's called. Text buff, comma, x. No. Yeah, it's text buff, comma, x, right? Yeah, I think so. And then that'll basically put it in the last character in the text buffer. So we're kind of filling it right to left instead of left to right because we're starting at 40. And then we want to decrement the x. And then we want to compare that branch if not equal to 0. No, branch if 0. How do you do branch if 0? Here we go. Compare x 0. Is that what we do? No, I think when we decrement x, it's already going to check if it's going to set the flag, right? So I think we can just do branch if not equal. I don't know. We'll have to check this. And we branch to f loop. Otherwise, we return from subroutine, right? Does this look right? I feel like I forgot stuff. Let's take a look. Let's compare how we did. So we have fill, load. Okay, so this doesn't really matter what order it is. You see, like they did LDX bufflen first, second, but I did it first, and then they do LDA fill CH second, whatever. We split. Start. They called it start. I called it F loop. Decrement X. Oh, so they decrement first. Then they do store text buff X. Branch if not equal to start. I don't think the order there matters between decrement and oh, it does, because yeah, mine is wrong because it's going to, it's like the length -1 issue. The length is 40, so we want to start with -1, so we should decrement first. They're right. But otherwise, the statements were correct. Text buff, comma, X. Start, they called it start decrement, store, branch not equal, floop. And the branch not equal, I don't think that is not affected by the store command. So it's basically looking at the decrement X command and checking if it is 0, right? All right, let's see here. This program is quite straightforward. Using indirect addressing and the X register countdown, it will fill each memory address in a text buffer with a designated fill character of fill CH. Then the program ends. The subroutine will work with any 8-bit fill character and with any buffer length up to 255 characters. Later on in this book, you'll find some 16-bit routines that can stuff values into longer blocks of RAM. You can use this routine by incorporating it into your visitor program. Let's do it first. Let's make sure that, oh yeah, we have to do the jump subroutine. But let's do it first to our response since that's what we're playing with. So let's list it. Text buff, open screen. Then we have bufflen 40, fill character 20. Oh, it's 20, not 21. So our 66 fill CH should be 20. Okay, fill CH is 20. We fix that. 9B, 650, text byte, blah, blah, blah. Load X0. That all looks right. I think all of that's the same. And then here we have our fill. We have this start, return subroutine. We need the part where we fill first, no? Jump infinity. So where do we actually go to fill? We're never calling fill here, so I don't know how. This looks wrong, right? You see here in the visitor program, they do jump subroutine fill right in the beginning, right before their loop. We don't jump subroutine fill. Yeah, so I think they made a mistake here. We need, right before we do this loop on line 160. Oh crap! I didn't save my code. I pressed F5. Oh my god. Autosave. God, how many times has that happened to you guys? Oh my god. I don't think we lost a lot, right? I think we did lose some. We lost some, guys. Oh my god. Well, what can you do? We can cry. Bufflen equals 40. 66 fill character equals 20. We did that before, right? And then I think what I was saying is in line 155 we should do jump subroutine fill. Otherwise we'll never start it. And then yeah, I sound so sad, right? I don't remember what I wrote exactly, but it was like, I had it the other way, so I'm going to keep my stuff. I think just to show that it doesn't matter. And then here I called it F loop, right? And 340, I realized we should decrement X. 350, oh no. This needs to be 2 characters, decrement X. 350, store the accumulator, which should be the fill character, into the text buff, comma, offset by X. And then 1360, branch not equal to floop. and 1370 returns to subroutine. Let us save this. resp2.source. Okay. Let's try to compile this. The code starts in 66B and it ends in 691. All right. So that should be all assembled, although we didn't assemble the first program, so we should do that. Let's do that now. Enter D2 print screen 2 dot source, is it? Hey, please no username. Yeah, I think this was the right one. We will assemble this. And then we'll also load our last one just in case. It was called resp2.source. And we will assemble that. And now we'll run it in our debugger. G66B. I am the leader, you fool. And look, it has spaces. It works. I'm pretty sure that wouldn't have worked if we just did what they did, because they never call the fill subroutine. I feel like I'm trying to convince you guys I'm right. They screwed up. They needed to call the fill subroutine here somewhere. So good job on us to figure out that it's busted. But no more hearts. When you have both of these improved programs safely stored on a disk in both their source code and object code versions, you can run them and see that all of our difficulties with our text buffers have now been resolved. And that brings us to our next chapter, in which you will learn how to call assembly language routines from basic programs. Yay, guys, we finished chapter 7. Congratulations, everyone. I hope you enjoyed that as much as I did. Well, I really enjoyed it, except for the part where I deleted my code. Like, that was painful, right? But yeah, that was a lot of fun. We learned how to basically mostly print characters with assembly, to do loops, to do branches. There was one part that was still a little confusing, was that BNE. Let's look it up, because maybe it is useful to kind of just remember what it says here. Branch if not equal to 0, that was the BNE we used, right? And what was complicated is this. So I was making fun of it and it bit me in the ass. That instruction, BNE loop, which means branch to the next statement labeled loop if the 0 flag of the process status register is set. This instruction uses what can be a confusing convention. If the register 0 flag is set equals 1, if the 0 flag is set equals 1, if, oh, here it is. The 0 flag is set if the result of an operation that has just performed is 0, and that 0 flag is cleared. So when we decremented the X register and it became 0, then basically the 0 flag was set. Branch to the statement labeled loop if the 0 flag is set, right? So we sometimes do have to think of BNE loop as branch if 0 bit is set, because when we do decrement to X, we're not really checking if it's not equal, we're checking if it's really 0 bit is set. So it's kind of actually a bad thing, right? So branch if the 0 bit isn't set. and decrement x will set the zero flag. Where do we learn about decrement x somewhere? Probably somewhere else, but I'm sure it sets the zero flag when it gets to 0. All right. Well, this will be loaded as a VOD. So if you're watching this on YouTube, then please do like and subscribe if this was fun. There's a whole playlist for all the other chapters up to this. So if you're like, hey, looks cool, but I don't know what we're doing, go back to the first one, follow through, read the book if you want. There's all the links, all this stuff is available to you. I would love to hear that it's working for you guys. To the person who gave me the F8 hint, thank you so much. That was so useful. I now need the hint of like, how do I go back up with Altira? Like, I don't know how to like go back up and down with Mac 65 stuff. Like, how do I go up and down? So if I do 10, foo equals 3, how do I go back up to edit that? That's what I need to know, and then I'll be in good shape. So yeah, that's it. Thank you so much for hanging out with me. Hope you enjoyed that. Thank you all. Thank you all. Bye. And we'll continue later. I also do videos on like other things like Nix and Haskell and COBOL. Yeah, we got to do COBOL. Oh my God. COBOL's starting to stress me out. Like every time I get ready to do COBOL, I'm like, okay, hang on tight. It always feels like such a fight, Maybe it'll get better. Maybe I'll learn to love COBOL. But yeah, oh, yeah.